Hi, this is Steve Dettenberg. This is our second video discussing the force of friction, and in this video we will discuss energy considerations. Okay, so we are going to talk about energy. When we are doing energy computations, remember that friction is a force, and a force times the distance that it's applied is work. And work is measured in joules, just like energy is measured in joules. In fact, we had the work-energy theorem in mechanical energy that said the work applied to an object is the change in that object's kinetic energy. Energy, 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 and F times D is energy. So let's take a simple little situation. You have a mass on a frictionless surface traveling at a speed of v sub naught. So it has some kinetic energy, and it's going to travel across this frictionless surface, but it's going to run in to a patch that is rough, that has friction. And the coefficient of kinetic friction there is mu sub k, and the length of this section is d. And after it passes that, we want to know what the final speed of the mass is. Well, what's going to happen? As it traverses this distance, friction is going to apply a force on the mass opposing its velocity, and that force times the distance is the work that friction does on the mass. And that work will eat away at the energy of the mass. And where will that energy go? That energy will generally go into thermal energy. It will no longer be available as part of the total mechanical energy of the mass. The mechanical energy being its kinetic energy and its gravitational potential energy, and if there's a spring, the spring potential energy. This energy that is lost through friction disappears from the mechanical energy stores of the mass. And energy is force times distance. In the following playlist, when we talk about momentum, and you've probably studied this already, force times time is impulse, and that is a change in momentum. But the losses due to friction go to thermal energy, not thermal momentum. So use energy when dealing with friction. So what do we have? We have the initial energy is 1/2 mv sub naught squared, and the final energy is not the same. The final energy is 1/2 mv final squared, and that's going to equal the initial energy minus the loss of energy due to friction. And that should be very obvious and make perfect sense to you. At the end, we will have what we started with less what we lost. So going back up to our diagram, once again, you have the mass coursing across this rough area. The normal force on the mass from the ground is mg, and the force of kinetic friction is the coefficient of kinetic friction times the normal force, which is mu sub k times mg. And that times d lets us write 1/2 mv sub naught squared minus mu sub k mg times d equals 1/2 mv final squared. And this should just make perfect sense to you. And if you want to do the algebra and come up with an equation that says v final equals, you can go ahead and do the math if you like. So, now, this is the most important part of the videos on friction. In the past, like all through the energy playlist, I said we always start with this equation. The energy initial equals the energy final. And we work things out from there. and we were always dealing with conservative forces. So we had a block that was going to follow some path, trading potential energy for kinetic energy, and end up someplace, maybe with a certain velocity, a certain gravitational potential energy, and this equation would rule. But now we have a very important addition to our standard always start with this energy equation. We're going to say the initial energy plus the work done on the system equals the final energy. And by this we mean the work done by non-conservative forces like friction, or perhaps by external forces that are not part of the system. But almost always it's going to be friction, the friction non-conservative force. And I'm being better here about using the sign, because really when we had that situation of the mass running across the rough spot, the friction force was in this direction. This is our positive direction. The friction force is moving in the negative direction. So the work was negative. We're adding a negative work. Think about it again. The energy that you end up with is the energy that you started out with plus any changes that happened. And as we said, the changes will usually be friction decreasing from the energy that you started out with. It should make perfect sense, and if you understand it well, you'll never write it down wrong. Now, I want to take our problem here, this problem, and change it just a little bit to make a point, and that little point and the understanding of this equation is going to make the first free response question that I discuss toward the end of this particular playlist on friction absolutely trivial. So the new problem, almost identical to the old. You're starting out with the mass, moving at v sub naught. It's going to roll over a rough patch that has length d and will provide friction. Mu sub k is the coefficient of kinetic friction. And when it passes the rough area and gets back to the friction-free area, it's going to go up an incline that has an angle of theta to the horizontal. And assuming it had enough energy to get past the rough area, it's going to rise up and up and up, and it's going to stop somewhere. It's going to run out of gas and it's going to stop. And the question is, if this distance is s, how far up that incline did it get when it stopped? This is a trivial problem if we write our equation. We're going to say that the initial energy plus the work done on the system by non-conservative forces or external forces equals the final energy. And then the next line that we always write, the initial energy is the potential energy, which let's write it all out here. It's the gravitational potential energy plus the spring potential energy, and also part of the initial energy is the kinetic energy. These are the three components of mechanical energy that we discussed in the energy playlist. That plus any changes to the energy, which we already know will be a decrease in energy from the friction, equals the final energy, and the final energy will be the same thing. Gravitational potential energy plus spring potential energy plus kinetic energy. Now, most of this we already know. In the initial situation, the gravitational potential energy is 0 because there's no elevation. We'll consider this our reference plane. There's no spring potential energy because there's no spring. And the kinetic energy is 1/2 mass v sub naught squared. The work done on the system is negative work from friction. And that's the friction force times the distance under which it was operating. And that's mu sub k times the normal force, mg, times d. And that equals the gravitational potential energy, which is mgh, where h is the vertical elevation against gravity that the mass achieves, plus 0 for the spring potential energy, plus 0 for the kinetic energy. Because when it comes to a rest up that incline, the kinetic energy is 0. And that seems simple, but that's an important point. And there's just one more thing to figure out, and that's the relationship between S that we were asked for and H that appears in the gravitational potential energy. And we know that H over S equals sine of theta, so H equals S times sine of theta. Now let's plug it all in and have some fun. 1/2 times the mass times v sub naught squared minus, this is minus because this work is working against us, minus mu sub k mg equals mg times h, which is s, times sine of theta. So, as happens so frequently, we can scratch out the mass from every term, which means the answer will be unchanged if we change the mass. And also, as is very common, note that we cannot remove gravity from every term because gravity is not involved in the kinetic energy. So let's rewrite this. 1/2 v sub naught squared minus u sub k gd equals s times g sine theta. And we have s equals 1/2 v sub naught minus u of k gd all over g sine of theta. And it's just like every other problem. It's a little bit of understanding and then some 8th grade algebra. Let's take a look at a couple things before we move on. Our answer seems to make sense because according to the right side of this equation, if we start out with a higher velocity, s will be higher. If the coefficient of friction is smaller, let's say it's 0, then once again, s will be higher because we will lose less to friction. If the force of gravity is higher, s will be smaller. And if sine theta is smaller, meaning a smaller angle, if this denominator gets smaller, then s will be higher because with the smaller angle, the mass can climb farther up the ramp. And let me point out again that when the mass gets to the top of the ramp, the kinetic energy is 0. And as I said in the first FRQ that we do, that's really going to help us. Just a couple things to do before we quit. Now it should be trivial for you to work this problem that we're not even going to work. A mass starts out with a certain velocity, and then it hits a field that goes on and on and on, where there is friction, and mu sub k is the coefficient of friction. And the question is, how far into that field will it get before it stops, before it runs out of energy? Well, we really should write our equations. In fact, I wasn't going to, but let's do it. The initial energy plus the work done from non-conservative forces equals the final energy. And the initial energy has no gravitational potential energy or spring potential energy. It has the kinetic energy. And the final energy is just 0 because it doesn't have any gravitational or spring potential energy and it's run out of kinetic energy. And the work done is negative work from friction. So that's negative work, and that would be mu sub k times the normal force times the distance that it travels before it poops out. And that equals 0. And through that, you can get the distance. And I want to work just one more problem. If you see friction from all of these different angles, it will all just be second nature to you. Our last problem, surprise, involves a wedge. Here's our angle theta. This is the height of the wedge. I'm going to tell you that the length of the wedge is d, although you could have figured that out from the height and from theta. There is friction along the wedge with the coefficient of friction of mu sub k. There is a mass of mass m sitting at the top of the wedge. And the coefficient of friction is small enough that the mass is going to slide down, it's going to come off the wedge, and it's going to head this direction on a frictionless surface. And we want to know what is its velocity at the bottom of the wedge. Now, what's the first thing we do? We write the equations that we always write. I'm telling you, if you write these equations, it's going to help. The initial energy plus the work done on the system from non-conservative forces, which is usually going to be friction and usually going to be negative, equals the final energy. We'll forget about springs here. We'll say the initial energy is the gravitational potential energy plus the kinetic energy. And then we add our work done, and that equals the gravitational potential energy that's final plus the kinetic energy that's final. The gravitational potential energy we know is mgh, but we're going to use d instead of h because we're using d for other parts of this as well. So coming up to the diagram, we have h over d equals sine theta, and so h equals d sine theta. So the gravitational potential energy is mg times d sine theta. The kinetic energy is 0 because it's not moving at the beginning. The work from friction, we'll figure that out. The gravitational potential energy at the end is 0 because if we call the gravitational potential energy at the beginning mgh, that means that this is our reference plane, and here it is at 0, and the kinetic energy that's final, well, that's what we want to figure out. And when we figure out the work, we'll have the kinetic energy because we have everything else. So let's see what's going on with our friction. We have gravity pulling down toward the center of the Earth with the force of mg. The component of that gravity that is perpendicular to the surface is offset by an identical normal force, and that's mg cosine theta. The component of gravity that is parallel to the surface is mg sine theta, and there is a force of friction that is opposing the motion of the block, that is the coefficient of kinetic friction, because the mass is moving, times the normal force, which is right here. And the work done by friction is negative, and it is eating away from the energy of the system. And work is force times distance, and that will be the friction force times the distance that the mass slides down the wedge. And that is mu sub k times the normal force, that's the friction force, times d. And since the normal force is mg cosine theta, the energy taken away from the system is mu sub k times the normal force times d. So our equation now says mg d sine theta minus mu sub k mg d cosine theta equals the final kinetic energy, which is 1/2 m v final squared. We'll scratch out those m's, and I'm going to multiply everything by 2. We'll say 2g d sine theta minus 2 mu sub k g d cosine theta equals v sub f squared, and we're there. V equals the square root of everything on the left above. 2gd sine theta minus 2 mu sub k gd cosine theta. 8th grade algebra. But let's play with it just a little bit, okay? Let me do this. I'm just going to rewrite it. V equals the square root of 2gd times sine theta minus mu sub k cosine theta. See that? And let me write it once more. V equals the square root of 2gd times the square root of sine theta minus mu sub k cosine theta. I'm doing this for a reason. It won't be mandatory on any test. But let's just take a look at this. If mu sub k is 0, if there is no coefficient of friction, then there's no friction, then this term will go away, and we'll be left by saying V equals the square root of 2g d sine theta, which is the same as the square root of 2gh, which if you go back to the first of the energy videos, you will see that this is the velocity of a mass if you just drop it straight down for a height of h. So that should make sense. Let's take a look at a couple of coefficients of friction. In this chart on the left, we have what two surfaces are moving against each other. And on the right, we have the coefficient of static friction and the coefficient of kinetic friction. We've said that the coefficient of static friction is typically larger than the coefficient of kinetic friction. And we see that all up and down this table. The coefficient of static friction is high when you expect there to be a lot of friction, shoes on wood, rubber on dry concrete. And when you expect there to not be much friction, it's very small. Shoes on ice, Teflon on steel, very small coefficient of static friction and of kinetic friction, which means that with these two surfaces moving against each other, friction cannot develop a large force. That's what the coefficient means. So the coefficient of kinetic friction defines the exact amount of force that friction is applying against the applied force against the motion of the object parallel to the surface. The coefficient of static friction defines the maximum amount of force that friction can apply to an object that is at rest on the surface. And it might be less than that amount if only a small force is being applied to it. Remember that? If you have a box on a surface and you apply a tiny force to it, friction will only put a tiny force against it to keep the net horizontal force zero and the box not moving. You can apply a bigger force and then friction will apply a bigger force. So it can be less than mu sub s times n. But once you apply a big enough force, then the box starts to move because mu sub s times n is the maximum force that friction can apply in a static situation. Now let's look at a couple of the pertinent equations on the page of equations that you are given at the beginning of the AP Physics exam. This one right here. The friction force is less than or equal to the coefficient of friction times the normal force. So they're saying that this is the friction force and this is the normal force. Now we know if the object is in motion, the friction force is going to be equal to the coefficient of kinetic friction times the normal force. They're calling this the normal force. So this equation as written is really for the coefficient of static friction, because it's the static friction that can be less than or equal to the coefficient of friction times the normal force. The other equation that applies to our discussion is this one, that the change in energy of a system, which is the work done on the system by non-conservative forces, is equal to the force of that non-conservative force times the distance through which it's applied. And we've seen that in a number of the problems that I've worked. Now it says times cosine theta. And we've seen cosine theta in work equations before, because we said if you were pulling a box across the floor and you're pulling in this direction and the box is moving this way, let's say without any friction, well, the work you are doing on the box is the component of your applied force that's in the direction of motion. So if this is theta, we said the work you're doing on the box, and we said this during the energy chapter, equals the applied force times the distance the box moves while you are pulling it times the cosine of the angle between the movement and the applied force. That's when we said that someone who pulled the box across the floor, if he was pulling in this direction, he pulled and he pulled and he worked and he worked and he did succeed in dragging across the floor, but he didn't do a gigantic amount of work, because the only work that he really did was with this horizontal component of the big force that he applied, and that's F cosine theta. Now, with all the problems we worked with friction, we had some object moving across the surface. It was moving in a direction, and so friction was always opposite that direction, so there's no angle. So we said the friction is doing negative work on the object because it's opposing the object's speed, and the work it does on the object is the force of friction times the distance through which that force was applied, the distance through which the object slid over the rough surface. So in our equation, we said the initial potential energy plus the initial kinetic energy minus the work done by friction equals the potential energy final plus the kinetic energy final. We said actually that it was going to be potential energy initial plus kinetic energy initial plus the work done on the system equals potential energy final plus kinetic energy final. And then we said this is the general form of it. But specifically for our purposes, the work was friction in the negative direction. And the work turned into negative friction force times distance. So actually, not to confuse you too much, but it really is the case that we are using that cosine of theta, because if the box is moving this way, and the work done on the box is the force of friction times the distance through which it's applied, times the cosine of the angle between the motion and the force, well, the motion is this way, and the force is this way. So the angle between the motion and the force is 180 degrees. So we can say the work done on the box is the force of friction times the distance through which it's applied times the cosine of 180, which is -1. And that's where that negative comes from. And we can say minus the work done on the box by friction. We just knew intuitively that it was decreasing the total energy of our system, but this justifies the use of the cosine. If that wasn't clear enough, drop me an email. This is Steve Denenberg. Leave comments or email me with any suggestions. And thank you for your attention.